Okay.
PowerPoint. if you
Yeah.
want to know.
Okay. Start.
Okay, so today I'm going to be talking about TBARS, which is thiobarbituric acid reactive substances, and this is a way the food industry, lab work, any sort of industry dealing with fatty acids, they can measure lipid oxidation. So just going through some basic. So lipids, it's an encompassing term. You can break it down into a couple different categories. You have fatty acids and glycerides. You have free fatty acids, which is just your, right here, you have cholesterol, triglycerides, the glycerol backbone with 3 fatty acids, and phospholipids, which is the phosphate head, glycerol backbone, and 2 fatty acid tails. When I did my research, I did a lot with phospholipids and krill oil, which have highly unsaturated fatty acids, which in turn plays a big role in lipid oxidation. So, like I said, fatty acids play a big role in lipid oxidation because the more unsaturated a fatty acid is, the higher susceptible it is to oxidation. So, 2 of the big ones you hear about most commonly are DHA and EPA. Highly unsaturated, very long chains. In your fish oils and your krill oils that are used kind of as supplements, those products are highly taken care of, and a lot of additives are added to, like the pills or whatever you have, to create an environment that will block out light and block out oxygen, which are big proponents of lipid oxidation. So we have, like I said, saturated versus unsaturated fatty acids. Saturated ones are less susceptible to lipid oxidation. And you can have your different omega-6s and omega-3s. And if these lipids are oxidized, then they no longer offer any nutritional value. So when you have food products, you want to protect them as much as you can. So this is just a little diagram that shows the lipid oxidation process. It is very complex. It is highly studied in the food industry, in chemistry, biochemistry, all sorts of industries, because it is not fully understood yet, especially the initiation step. But the gist of lipid oxidation is you have an unsaturated fatty acid, comes in contact with oxygen, and this reaction happens via a free radical mechanism. Again, still a very complex explanation, but that's like a simple explanation of it. So looking through this process here, you end up with this lipid peroxide as the final product. However, this final product is highly unstable, so it's quickly broken it down into secondary products. And the secondary products are important because they can cause your food products to become rancid, change colors, all flavors, all kinds of issues. And this is also pretty big in the meat industry. So they study a lot of lipid oxidation in beef, because you know there's a lot of fats and stuff like that. So this can cause your meat products to become rancid very quickly. The secondary products are also important if you want to measure your lipid oxidation, because MDA, which we'll get into in a second, is the type of secondary peroxide that we're going to measure in this assay. So like I said, oxidation of food happens. It can cause your food to be spoiled, or however you want to call it, in no time. You have 3 types of oxidation. Autooxidation, which is the main one, where unsaturated fatty acid and our oxygen breaks down into this peroxide. Photooxidation, which is when a product comes in contact with light. That's why a lot of things may be stored in foil packets, or like melting a colored jug to prevent any of these issues. And you also have enzymatic. But autooxidation is one of the main causes of meat to become rancid, other than microbial degradation. So it is a huge issue. And it starts from the point of harvesting your food, whether it be slaughtering cattle, picking a fruit, or whatever it be, to the point of consumption. So there's a lot of steps taken in there, such as antioxidants added to processed foods. We vacuum package things in, like I said, foil packets or colored products. You have a lot of oils in green or brown bottles. That's to prevent photooxidation, and cold storage. So unsaturated fatty acids are more likely to be oxidized at higher temperatures. This can play a role in your krill oils and fish oils. They're kept frozen until you use them or whatever, or more highly processed to prevent more lipid oxidation. And just going over some of the effects, like I said, you can have loss of nutritional value if these things are broken down. The sensory quality is greatly diminished. You have a nice pink product. It will quickly look brown. It will have an off smell, off flavor, and you can't sell this product, so you're going to lose money. Also, these peroxides can be toxic in the body, so we don't want free radicals and all these kinds of things just floating around, and it can be a lot of negative effects. But one benefit of lipid oxidation is dried cured meats. So you want to hang your beef and let oxidation happen. That kind of creates more flavor in your meat and things like that. So that is a plus side to oxidation, but there are many, many negative sides. Okay, so TBARS, which is the barbituric acid, is used to measure the state of lipid oxidation in your product, whether it be tissue, you can do blood and urine samples. It can be used for a wide range of products. So this acid, the TBA acid, reacts with MDA. And the MDA is one of those secondary products that I was talking about earlier. It's the most commonly used marker for oxidation, and we'll get into a little bit of that later. So when you have a product and you introduce this TBA, they create this adduct, which is shown right here. And then after this reaction happens, you can measure the amount of that adduct by colorimetric or fluorometric assays, which is, we'll go into that a little bit later too. So a little bit of overview of the methodology. First, you typically want to create a standard curve. So this type of assay will come in a kit. They'll give you everything that you need, the acids, anything else that you need, and you will mix your sample with your MDA, do everything, and then to create your standard curve, you'll have known concentrations of your MDA, run the reaction, and then do the results measurement, and this will give you a graph that I'll show you later, and then you can kind of use this graph to determine the concentration of your unknown samples. Also, it's important when you're doing these reactions, you flush your vials with nitrogen because you're going to be heating it. So this adduct is formed at a higher temperature. And like I said earlier, higher temperatures increase oxidation. So you want to flush it with nitrogen, which will lower the oxygen in the tube, therefore limit further oxidation just from the acid. It is a very complex process. It doesn't sound like it, but you can have a lot of varied results because of so many steps in the heating and the different, you're adding acids, you're adding everything that can play a role in just breaking down your sample to begin with. So once you get your results, you have a couple different ways of measuring. You have the MDA equation, which I'll show you in a second, colorimetric, which is just observing the color change. So what is this video real quick? It's not a great video, but it shows you when this adduct forms at a high temperature, it changes color, and that's how you can measure the color change to determine the concentration of MDA. So if I want to just show you over time how this is changing from clear to pink or red, and then we'll get into measuring that. There aren't a lot of YouTube videos about these types of assays. So you can see here the difference of the beginning to end of the color change. So based on that color change, and these are the curves you can get from running your standards. There's also an equation you can use, and this is taken from a previous PhD student here, Derek Warren's paper. He ran this type of assay for his research. And there's also another way to calculate your MDA concentration. Another fun video. This is just another type of equation. If you don't do the standard curve. We're just going to skip right to it then, if you can't hear it. So this takes into account the moisture content, the overall lipid content, and then it has an equation to calculate everything out. It is a way more complex than just running your standard curve, finding the slope formula for that, and then plugging everything back in. To me, I think it's easier just to run your standard curve. Then you have great measurements to know specifically what's going on with your machine, how it's measuring things, and then, like I said, you can just kind of plug it into whatever formula you use and find your results. So there are a lot of shortfalls of this method, even though it's the standard method for measuring lipid oxidation. Because that peroxide, the primary product, is broken down so quickly into a bunch of different secondary products, this acid is not specific to the MDA. So it could be binding to all sorts of other aldehydes and things in the product that may have nothing to do with lipid oxidation. So if you want specific MDA concentration, you might want to do something like HPLC or other chromatographic measurements, although those are way more complex and costly to even find someone that has a machine, set up a method. And it's more time consuming because you have to do all that stuff. So if you just want an overall general idea of lipid oxidation, TBARS is the way to go. But if you're doing something that has a colored pigment in it, during this extraction process, you can extract some of that color. So if you're doing like a colored oil, like acryl oil is that super red, dark colored, well, your product is red, so if you extract any of that color, it's going to alter your results. So if you're doing something like that, you may want to look into other options or ways to not extract the color, but only the lipids. So that's just something that you have to think about if you're doing something like this. So this is just an example of some results from an actual TBARS assay. This is from Derek Warren's master's project, I think. He did the shelf stability of a sarcoplasmic protein powder compared to a whey protein powder. Sarcoplasmic protein is a water-soluble protein that they extracted from silver carp, which has that pink color. And they stored it at different temperatures for 9 months. And like I was saying earlier, the lipid oxidation can also cause color changes and other off-putting flavors and things like that. So I don't know if you can see in this one here. This is, you don't have a lot of change in lipid oxidation in his product. That's because they were sealed, vacuum sealed in foil packets, so they were no oxygen, limited light exposure, which again, this demonstrates those types of things will help protect your product, even though they were kept at higher temperatures. But there was a significant change in the whiteness. So a measure of whiteness is like how light a product is. So at the start, at the start, you have your initial measurement of whiteness, and over time, it gets less white, if that makes sense. So you'll have more of that browning and change of color from any sort of oxidations. And this is like a high protein powder, obviously, so there's a lot of different oxidations that are happening. But this just shows you there's a degradation of a product, even though all of those measures are taken, like the vacuum packaging and the limited life exposure. And this is a paper that we're currently trying to get published, but we'll see how it works. All right, are there any questions?
Questions?
Great, I love no questions.
Thank you, Casey.
Okay.